Okay, hello everyone. I'd like to welcome you all to our fifth Club Talk webinar series. I'm Dr. Oluni Fadare, and I'll be moderating this program. I'm a member of the PAN-microplast team, and this is a network that promotes, facilitates, and encourages lateral collaboration and research effort, as well as knowledge exchange in micro, nano, and plastic pollution in Africa. I would like to introduce our speaker for today in person of Christian Ebere Enyoh. He is currently a research fellow at the Department of Chemistry, Imo State University, Nigeria. He holds a Master of Science degree in Analytical Chemistry from the same university. His research is currently focused on micro and nanoplastics and other emerging pollutants, including their monitoring and remediation. He led a research which provided for the first time in Nigeria the impact of micro and macroplastics in soil on phytochemicals in plants. He's a member of the Chemical Society of Nigeria and has over 95 publications to his credit. We only have an hour for this program. Christian will make his presentation titled Application of Index Model for Assessing Freshwater Microplastic Pollution, after which we have our question and answer section. Please be informed that this webinar will be recorded for academic purpose. Our YouTube channel also will become active, and you can watch this presentation or any of our past presentation on the platform. Now, let's join Christian Ebere as he gives his talk. Christian, you have the floor.
Okay, thank you, Doc. My name is Christian Ebere. I'll be talking about the application of index models for assessing freshwater microplastic pollution. I'm affiliated with the group research in analytical chemistry, environment, and climate change at Imo State University. So it is no more news that we are experiencing the problem of plastic globally. Personally, I fell in love with plastic research after the United Nations Environmental Program, like 2018, beat plastic pollution. So the amount of plastic that is reaching our environment is on the rise globally yearly. In 2020, data showed that there are 5.25 trillion microplastic in our oceans. So why this plastic in the environment, they cause so many problems, such as maybe getting consumed by aquatic life and even humans, where they can cause some diverse health effects, including particle toxicity, where they accumulate in the body system, and maybe with associated biofilm, where they trap pathogens, and chemical toxicity, whereby they leach chemical present in the plastic, or when they absorb pollutants from the environment, other pollutants such as organic matter, organic pollutants, heavy metals, before being consumed by the body. So in the figure that I displayed here, we can see that plastic pollution problem. The first figure was actually taken from my streets. Was actually taken in my streets. Was actually taken in my streets, and why the other one is showing that plastic polluted by single use. So because of the problem of plastic we're having in the environment, many studies keeps coming every day, different kind of studies of plastic every day, every month actually. So most of the studies that are coming out daily, there has been some kind of difficulty in comparing them because of lack of standardized analytical methods. Some study could use the micro Raman, some could use the FTIR, some could use the SMEDS. And when you're using this different methodology, you can actually get, it's difficult to actually get exact results, even when you're working on the same sample.
Hello, Mr. Christian, please. Yeah, we're having a feedback from you. Can you adjust that? There's echo from your side.
Feedback?
Yes, there's a background feedback that is not making your voice to be clear. Okay. Yeah, a lot of our attendees are having problem hearing you.
Okay. Can you hear me now?
Yeah, great.
Okay, I'm saying that because of the issues of plastic pollution and microplastic. Numerous studies keep coming out almost every month. And some of these studies is quite difficult to compare among them because of lack of standardized method yet. There are many methods that people have been applying in the study of microplastics and the reporting units. On this slide, you can see that there are different methods like micro Raman, micro FTIR, microscopy, etc. These are different methods in analyzing microplastic in a particular matrix. And because of the difference in methodology, some results can actually, someone can get the same results, and it's quite difficult to compare those results. In the same way, the reporting units, some studies report in mass, some report in number of particles, and so this difficulty in comparing results is another problem we are experiencing concerning microplastic studies. So why do we need index models to analyze microplastic? So index model is an algorithm that gives a single number as the final result from measured variable computation, thereby expressing a measure of the qualitative state of the particular media that has been analyzed. And index models can actually help us to beat the problem we are experiencing with comparing results from different studies. If someone should study a particular media using a particular methodology and apply models on that data obtained in that study, another person study maybe microplastic in another river and apply these models also. Somebody can actually compare them easily because the models is not sensitive of the units that is used to report the data obtained. So some of the advantage of models is it gives precision and direction for problem solution. And information from models is viewed as simplified concepts of environmental issues. So you don't have to crack your head too much. You just apply, get your data, put it into models, and get a value which can enable easy comparison across studies. So policymakers can actually arrive at a conclusion concerning a particular environmental issue. At least it gives a probability and it helps predict a possible scenario of microplastic pollution in particular environments. So some of the models that can be applied in microplastic studies are categorized as those ones for contamination and pollution assessments, e.g. the microplastic contamination factors, and also the microplastic pollution load index. This one are used for contamination and pollution assessments. The first model is microplastic contamination factors, which is used to estimate the contamination level of microplastic in a particular river or freshwater. So that is done by comparing the microplastic quantity obtained with the background value. So the ideal background value will be that from a sample of MP prior to a rapid development of plastic industry, which is quite difficult to obtain. So one of the ways to get a background value is to use maybe data from that particular area that show the lowest quantity of microplastic. So that data can actually be used as the background value for microplastic in that area. But the ideal value would have been to the prior development of plastic industry, which is quite difficult to obtain. So to get the microplastic contamination factor, you just divide the quantity of microplastic in a particular sample by the background value of microplastic. So you actually get a particular data, which cannot be compared, cannot be categorized based on the categories presented here. When the microplastic contamination factor is less than 100, we can say it is low contamination. When it's between 100 and 300, we can say it's moderately contaminated. And when it's between 300 and 600, we can say it is considerably contaminated. And when it's higher than 600, we can say it's highly contaminated. So the contamination factor enables us to determine how much contamination of the river is caused by microplastic compared to the background values. So the MPI is the quantity of microplastic in that particular sample from that particular area. So from the microplastic contamination factor, we can estimate the microplastic pollution load index. This one evaluates the overall pollution load of microplastic based on the quantity quantified in that particular sample, that particular area, which is very similar to the pollution load index proposed by Tomlinson et al. In 1960. So it's just very similar to the model. So this one helps us to determine how much load of microplastic is particular in that particular area. So if you have the microplastic contamination factor for a particular maybe sample, then you can have the pollution load for the particular area. So this is the category A of the index models. This one is for contamination and pollution assessment. Why these two models are based on the load, based on the quantity of microplastic. Then we can have the microplastic polymer risk indices and index. Indices is for the sample, while the index is for the entire area. The polymer risk indices evaluates the contamination of microplastics based on the amount of based on the polymer type. So if you have a sample that you analyze and you have maybe PP, PET, different type of polymer identified in the sample. So this model is used to estimate the polymer risk based on the different polymer identified. So from the model, that is equation 3, the PJI is the number of each microplastic polymer. So if you have a sample, for example, and the number of microplastic in that sample is 10. And in among
Mr. Christian, sorry for interrupting you again. Sorry for the interruption. We're having issues with your background noise, and it will not be good enough for people to miss out, in this lecture. It's very interesting. Maybe you can increase your voice. Yeah.
I beg you.
So you can also increase your increase your voice so that we can hear you better. Thank you.
Okay. Is it better now? Is it better now, Doc? Okay.
Go ahead.
Okay. So, like I'm saying, I said that the equation 3 is for the microplastic polymer risk indices, which is based on individual sample. If you have, for example, a particular sample and the number of microplastic identified in that sample is 10, you have 10 microplastics identified in that sample. And among this microplastic quantity you identified, you have different polymer type. For example, PP, PET, PVC, etc. So now the HI, which is that's in equation 3, which is the polymer risk indices, is the quantity of each polymer type, that is PJI, divided by the total number of microplastic identified in that particular sample. If in that 10, if you have 10 microplastic and maybe 3 is polypropylene, so you have, for the polypropylene, you have 3 divided by 10, which is the overall, times SJ. The SJ is the chemical toxicity coefficient or risk scores. How do you determine the risk scores? The study of Littner et al. 2011 has provided hazard scores for different polymer type. So you have the PJI, which is the quantity of maybe the particular polymer identified, divided by the total number of microplastic in that particular sample, times the risk score for that particular polymer. Some of the risk scores are presented in the next slide. These are some of the risk scores presented in this slide by Littner et al. 2011. So these risk scores are based on the toxicity level of the particular polymer. So in the study of Littner, it presented up to 50 different polymer risk scores. So those risk scores will now be multiplied by the PJI divided by the MPI to get the HI for that particular sample. Then you do for the different polymer identified. And like I said previously, for PP, you calculate. For PET, you calculate. For PVC, you calculate. So you have values for each of them, or you sum them together. Once you sum them, you have your HI, which is the summation of the individual polymer divided by the quantity of microplastic identified, that is total quantity, times the risk scores. So that way you get your polymer risk index. So now you have for a particular sample. So now to now calculate for the entire area, you multiply, you use equation 4, which is for the entire area, which is calculated as the nth root of the individual risk, the polymer risk indices for the individual sample, individual polymer. That is the product of the individual polymer. So when you get your risk index, according to Cabell et al., the classification is provided here. When it's less than 150, we consider it low. When it's medium, is when it's between 150 and 300. It is considerable polluted when it's between 300 and 600. It's high when it's between 600 and 1,2. And it is very high when it's greater than 1,2. So why is this polymer risk indices very important? In figure 3 presented here, we can see that we know that monomers are what form the polymer. And in the production of plastic, there are other additives that's been added to maybe to strengthen the strength of the particular plastic. When these plastics are in the environment, they are likely to emit these monomers and these additives when they are degrading over time. So that is why these models is very, very important. When they emit this in the system, maybe drinking water, and somebody consumes this drinking water, there are double danger being posed to the individual that is consuming this drinking water. Because from the additive, that is the monomers as well, and another one is from the microplastic, the particle itself. So this helps us to estimate the risk of polymer. That is the polymer type. There is a composition of the microplastic to maybe ecosystem or maybe to health. So this is the importance of this model. So okay, this is the chemical toxicity coefficient or risk score for some common microplastic compounds. So this can be found in the study of Littner et al. 2011. Littner presented up to, I think, 15 different polymers. So then we have the microplastic pollution risk index. Initially, I thought that was the one I talked initially is equation 1 and 2. I talked about the microplastic pollution load index. Why this one is polymer? Equation 5 is based on the risk posed by the composition of the microplastics. So how do we determine this? The equation 5, which is the microplastic pollution risk index, that is for a particular sample, while the equation 6 is for the entire area. So for the particular sample, you have the polymer risk index, HI, multiply the microplastic contamination factor. So you calculate this for the different, maybe sample, to get the microplastic polymer risk index. Now for the entire area, you have the microplastic pollution risk index for a particular sample, you multiply them together, and you do the nth root, which is based on the number of sample or you are working with. Yes, number of sample you are working with. So this quantifies the pollution risk in relation to the composition of the microplastic polymer. So from the results you are going to obtain, you can classify them. Class 1 when it's less than 10, class 2 when it's 10 to 100, class 3 when it's 101 to 1,000, class 4 when it's 1,001 to 10,000, and class 5 when it's greater than 10,000. This is according to Ebere et al. 2021. Okay. So we can also estimate the health risk of microplastic as well. So equation 7 and equation 8. This is to calculate the estimated daily intake via injection. We already know that microplastics are ingested through maybe consumption of polluted water, or for example, maybe even because we're talking about water, yes, consumption of polluted water, maybe drinking water, or maybe when somebody is swimming or playing inside water that's contaminated by microplastics, somebody can have oral injection or oral uptake. So it is quite important for us to estimate the daily intake via injection. So we can calculate the estimated daily intake based on the overall quantity of microplastic identified, and we can also calculate the estimated daily intake based on the polymer type of microplastic. So equation 7 is based on the quantity of microplastic identified, while equation 8 is based on the different kind of polymer identified in the microplastic in the sample. So we can see the MPI is the average quantity of microplastic in the water times RI. RI is the injection rate, which is estimated as 2.2 liters per day for adults and 1.8 liters per day for children, divided by the body weight of the maybe adults or children. For adults, average body weight is 70, maybe for people in Nigeria, then 15 kilograms for children, maybe for Nigeria. So this data might vary for different countries. So we can use this to estimate the daily intake of microplastic. Daily intake for microplastic. So from the estimated daily intake, we can also calculate it via gamma exposure. People swim in water that's contaminated by microplastic, and this could expose them to microplastic through skin contact. So this equation 9 is used to estimate the estimated daily intake of microplastic via gamma routes. The MPI is already established, which is the quantity of microplastic identified in the sample. The PJI is the microplastic type, whether PE, whether polyethylene, and so on and so forth. The SA is the skin area available for contact. This data can be found from USEPA. The ABS is the thermal absorption factor, which is 0.001. The ET is the exposure time. The CF is the unit conversion factor. The GP is the pore diffusion coefficient. The pore diffusion coefficient will be calculated. I'm going to show that in the next slide. The AT is the average time, which is also given. So now to determine the pore diffusion coefficient is important because this microplastic, based on their size, could actually maybe pass through the pores of the skin, depending on the size of the microplastic. So the EDI gamma is also very important to be calculated. So how do we determine the pore diffusion coefficient? The pore diffusion coefficient is related to the pore diffusion coefficient is related to the absorbate coefficient, which is the microplastic coefficient when it's being absorbed through the skin, which is D. D is the molecular diffusivity of the absorbates divided by the tutorosity factor. Tutorosity factor is related to the absorbate diffusive in the pore to the diffusivity in the free solution. So the pore diffusion coefficient is estimated using equation 10. For some micropollutants, data for the D is available, but for microplastic, I do not see anyone in the literature. So equation 11, which is presented by Wick and Chang, can be used to estimate the molecular diffusivity of the absorbates, which is given in equation 11. The different parameter is already explained there. We have the phi value, which is a Greek word, relate the effective molecular weight of the water with respect to the diffusion process. This has a value of 2.6, the standard value. The M is the solvent molecule, because we're talking about water now. It's also provided. The T is the temperature of the water. The NV is the solution viscosity. And the VA is the absorbing molecular volume in centimeter cube per mole. The absorbate we are talking about here is now the water. It's not the water, because water serves as the medium which this microplastic will travel and get it in contact with the skin. So to estimate the tussicity is dimensionless, which is the length by which maybe the microplastic traveled in the water before coming in contact with the skin, divided by the actual length. If the microplastic is at a particular spot in the water and it travels round before coming in contact with the skin, so the length covered divided by the actual length that it should have traveled. So by using this, we can actually estimate the pore diffusion coefficient, which we will now be used here to calculate the EDI, the estimated daily intake gamma. So after estimating the daily intake, we can calculate the cancer rates of this microplastic. To calculate the cancer rates, the estimated daily intake multiplied by the cancer slope factor, which is the CSF. Each different polymer have their own cancer slope factor, but some of them are not yet dead. But some of the cancer slope factor available are presented in figure 6. So the vinyl chloride is 1.9. Vinyl chloride is the major monomer, information for PVC. Then for the ethylene oxide, for the PE, it's actually ethylene, which is not provided yet. For the PET, the major compound used in producing PET is the ethylene glycol or terephthalic acid. They are not provided yet. But ethylene oxide may be adopted because ethylene oxide is used in producing ethylene glycol, which is used in producing PET or used in production of polyethylene. For the PUR, it's also available is 0.24. For the acrylic nitride for PAN is 0.54. So this cancer slope factor will be multiplied with the estimated daily intake and used to determine the cancer risk of this microplastic, maybe via injection. For other pathways, maybe through inhalation, cancer slope factor are also available, and these models could also be modified for such a scenario. The MPCRT equation 13 is the summation of the cancer risk. So that can also be calculated. So application of this MP index models. So I applied them in my study published by the Environmental Analysis and Toxicology. So we analyzed these rivers for microplastics, and the data obtained in this study was used to test these models. So these are the quantities of microplastic in the different rivers identified. And these are the type of microplastic in the different rivers. This study is actually available online and can be obtained at any time. So this is microplastic contamination factor. Like I said previously, the best background value is from the time where before microplastic polymer industry becoming boom. So, but because of lack of that data in my study, this study, I adopted the smallest quantity of microplastic identified in my study, which was from the Okumpi River. Okumpi River is here. Yes, Okumpi River, which is the mean 9.5 from the upstream of the river. So this data was used as the background value for that particular area, Mangi local government area, which was used to divide the quantity of microplastic found in different rivers. And this is microplastic contamination factors. So we can see that they are quite low. They are low, judging from the classification I presented earlier. So for the polymer risk is from the different polymer type identified, the PE, PP, PVC, and PS. So once you apply that model, I have this result, the polymeric risk index. So the polymeric risk index is presented also in the figure 10, while the pollution risk index is also presented. The polymeric risk index, or how this is obtainable, has been described previously. The individual polymer defined a particular sample, dividing it by the total quantity of microplastic identified in that particular sample or area, as the case may be, multiply by the coefficient risk cause, that is toxicity coefficient number value, to generate the HI. So now the HI, now multiplying it by the microplastic contamination factor, you can get the pollution risk index. So from this area, we can see that they are very high. The polymeric risk index are very high. So the river would actually be toxic to aquatic animal or to health, human health, because people swim in these rivers. Then for the pollution risk, we have class 5, which is also very high. And why is this very high? It's because of the PVC that was obtained in the study. The PVC have a very high hazard scores, and the quantity of the PVC in the sample is quite high. So it's because of the PVC that is why you have high values for this. So I did not calculate for the estimated daily intake because these are rivers. If it's for drinking water, I would have adopted the estimated daily intake for this study. So, but to calculate the estimated daily intake is very, very easy also. The different parameters has already been described, and it's just to input data and press calculator, and you obtain your results. So what did I observe? In conclusion, there are no direct correlation between MP abundance with pollution risk. No direct, because a particular sample is highly contaminated by microplastic does not mean that the pollution risk will also be high. So it's not true. It's only the polymeric risk that correlated with the pollution risk. And also the increased MP pollution risks and levels were extensively studied with the presence of ample polymer. So based on quantity calculation for microplastic is not enough, but the polymeric risk index will give us more information concerning the risk posed by these microplastics. So the index models can enable easy comparison of microplastic pollution of different rivers or from different areas as well. And also the models can also be applied for different metrics. We can estimate it for maybe fish and estimate maybe microplastic bioconcentration factors, whereby we compare the data present in the fish compared to the one present in the water. So these are some of the references, and thank you.
Thank you very much, Mr. Enyoh. It's been a very interesting talk. Before I allow questions from our colleagues, maybe I should start to ask maybe 1 or 2 questions based on your presentation. I think from slide 10, I can observe something like daily intake of microplastics through DAMA.
Yes.
So I'm wondering if there is any study presently that has looked into the toxicity of microplastics through DAMA.
No.
Yeah. No, so how do we apply this model in when we don't have any data presently as regard the intake of microplastic through DAMA? Okay. And secondly, maybe you can write it. And secondly, between your slides 15 and 16, I want to know whether the model consider particle size to arrive at the risk indices and that of the pollution risk index. It's a known, it's a popular knowledge that the smaller the size of your microplastic, the possibility of higher toxicity, right?
Yes.
So do you consider that in this model? Yeah, those are my 2 questions, so that anybody that has questions can raise up his or her hand, so that Oli can bring them into the panel session. So you can attend to those questions before we take from our other colleagues. Thank you.
Okay. And the first question is how to apply this model for Dama. First of all, there are no studies yet, so but these models can be easily applied. The different parameters required in using these models are already available. The MPI is the quantity. The MPI is if you are going to calculate the EDI based on the quantity of microplastic you quantify in your sample. That is where you have your MPI. Then the PJI. That's why I said, I could written this equation in two form. The PJI is if you are considering the dermal exposure based on the polymer type. That one is settled. The SA is the skin area for contact. How do you use this model? You just only need to get the quantity of a microplastic. What is the quantity of a microplastic you have in the sample? You put here. You put it in the equation. What is this skin area available for contact? This is universal 18,000 centimeters square, which might actually vary with different countries. I don't know, but this is universal. This has been used in many studies of heavy metals. Then the DP is the pore diffusion coefficient. The pore diffusion coefficient is best to be calculated. For some micropollutants, there are some studies that have shown pore diffusion coefficient for some micropollutants. They are varies, but for microplastic, there are no studies yet. So this can actually be calculated, which I presented here. The pore diffusion coefficient is the dP equals to the D over the tortuosity factor. The tortuosity factor is dimensionless. How do you determine that? In an actual natural environment, it might be a little bit difficult, but it's very possible to be calculated. Because this tortuosity factor is calculated by the division of the distance covered by the plastic before actually coming in contact. Because when the microplastic are in the water, they can actually be floating like maybe moving banana motion, like they keep moving, and they covered a lot of distance, maybe before actually coming in contact with the person, maybe in the water, for example. So, but there's an actual distance whereby if the microplastic is standing maybe 2 meters, is in 2 meter distance from the person, it will actually travel in a straight line and covers that 2 meters. But it might not go in that direction. It might first of all float in different direction before coming in contact with the skin. So the distance covered by the microplastic divided by the actual distance it should have traveled, you get the toxicity factor. It can vary depending on that. The D can be estimated using equation 11. The phi value is 2.6, which is standard. Then we have the solvent molecular weight. We are talking about water here. If we are talking about oil, it's different. If we are talking about different media, it's different. The temperature is T, that is temperature of the particular media, that is of the water now, also plays a role because we know that temperature influences kinetic energy of the particular sample, of a particle in a particular matrix. Then the NB is solution viscosity. If the water is highly viscous, the movement of the particle might be quite slow compared to a water that have low viscosity. Then the VA is the absorbate molecular volume, which is in centimeter cube per mole. The absorbate here is the microplastic. What is the molecular volume of microplastic in the water? It's measured in centimeter cube per mole. That can be measured also. Then we can actually fit in all this data and get the value for D and use it, put in equation 10 and get the pore diffusion coefficient. And when we get it, we can actually apply it here. The BW is the body weight, which is already known. It varies by country. In Nigeria, we usually use 70 kilograms. And the 80 is the average time, which is also 70 years for an adult, then 6 years for a child. So when you have your data, your data for microplastic, you just queue it into these models and you get your EDI. When EDI are less than 1, we assume that there is no risk or low risk. But when the EDI is greater than 1, we say that there's high exposure via this dermal route. Same thing is applicable for the oral injection. I don't know whether I answered your question, sir. Doc.
Yeah, I agree with you. What I'm just curious about is, you are just using a general size, particle size for
yes,
the model,
particle
right?
size. So you can calculate for the different particle size.
Yeah, but in the real environment, we have various sizes and shapes, right?
Yes.
And you cannot really predict which one actually going maybe through the skin.
So it's best to calculate with the smallest size, because it's the smallest size that can actually, the skin size varies. Some skin pores could be as small as 20 micrometer. And there are particles that are quite lesser than that, which can actually fit in. So this dermal might be applicable better with very small microplastic. Very small.
All right, thank you.
Is it clear, Doc?
You're welcome.
Thank you. I also have a question. Thank you so much. I think although I think people struggled with the audio, I think your slides are clear. So for everyone who did struggle, you can go back and look at the slides, because I think that there's quite a lot of information that can help with that. I'm quite interested in the first two models, because obviously I don't really work with dermal and intake and things like that, but I work with microplastics in the environment, and this idea of baselines, it's so tricky. Like you said, it's really tricky to figure out what one country's baseline is compared to another country's baseline. And if we want to make these indices comparable across countries and across the globe, would it not be better to maybe use the sediment cores that people, I mean, there's not that many studies that are looking at sediment cores, but with these sediment cores, you could potentially choose a global baseline, everyone to use that, and then the index would be more comparable with each other, because I think with changing indices, it might not be comparable, and then we'll have the same problem as if we were using. So I don't know what your thoughts are on that.
No, I agree with you, though. I agree with you clearly. Because the major issue concerning this model is to get the background value. Background value. So, but what you're suggesting is quite obtainable, and personally, I think it's very, very good. So I agree with you.
I don't know if there's any questions from the audience. Please feel free to ask in the Q&A session. I know Steve has already made a comment saying that it was really interesting and superb talk, and thanks for the presentation. If anyone else would like to raise their hand, otherwise, while we wait, I do have Elvis. I don't know, Elvis and Athena, if you guys have anything. I do have one more question.
Okay. But I just want to add that presently we don't have enough analytical technique to really discover the nano-sized particle of microplastic in the environment. And this model seems to consider, the background microplastics, in arriving at the conclusion. I'm just wondering, for those ones that we cannot quantify presently, how do we go about that using this model?
For nanoplastic, did you say?
Yeah. Do you get my question?
No, I didn't get it.
Yeah, I'm saying that, for instance, still talking about the issue of intake to derma.
Okay.
We believe that most of the time it is the nano-sized particle that will definitely be involved in that. You don't expect the macro size or the meso size to be used in calculating.
Yes.
Yeah. So how do you apply that? Putting all those into consideration, that presently in the real environment, we cannot still quantify the nano-sized particles.
Yes, since we can't quantify the nano-sized particle yet, we have to wait to see when we can be able to quantify it before we can apply this model.
Yeah, arriving at the conclusion that this is this constitutes a risk to the environment, or if you're assuming in a pool You know, you're in the
Yes.
swimming pool. How do you arrive at that? Most of the swimming pool, you cannot really estimate the nano-sized particle in them now because of the analytical challenges. So how do you arrive at such conclusion, you know, using this model?
In my presentation, I didn't apply this model.
Okay.
I didn't apply it. So, but I'm showing that this model could actually be used. So if somebody could actually quantify nanoparticles now, then this model can be applicable. Initial idea was low quantity, small size, very small size of microplastic can actually be fitted. Those small size that can actually pass through the skin, very small. So, but because of the difficulty in quantifying them currently, that these models might actually be kept pending before it can actually be used. But I'm showing here that we can actually use this to estimate thermal exposure. How do we estimate it? If you can get the data for the nanoparticles, for example, very small microplastics, we can actually estimate the thermal exposure using these models. In my presentation, I didn't apply the model, but I'm showing that this is possible because the whole. Okay.
Yeah. Oli, please, can you allow Spark to ask this question? I can see him raising up his hand.
Yes, Conrad, you should be able to ask your question, and then after that, we do have other questions. So,
sure.
Conrad, hello.
Thank you. Yeah, thank you very much, Holly. Thank you very much for the presentation. Found it very, very interesting. Doc, you had a slide relating to the number of microplastics reported in the rivers. I'm not sure if it's the next one or the previous one. The total number of microplastics. I think PET, from what I can recall, was the highest.
Slide, please.
The one with the number of microplastics measured in the river.
Yeah, your data.
Yeah,
I guess. Yeah.
That one, yes. It's a particle. The one to the right is particle per liter, and PET is about 450. Now, with the polymer risk index, did you measure all 450 microplastic particles to identify the polymers? Because literature often refers to 5% of representative microplastics to do polymer identification. I'm just wondering if you measured every single microplastic particle to identify the polymer, or did you take representative samples from which
you use data.
The risk index? Thank you.
Okay, yes. To calculate the polymer risk index, this is the equation. Let me go back to that equation and show. That is equation 3. The summation of, you calculate for the individual polymer. That is, if you have PET, you have PE, you have PVC, you calculate for the individual polymer and you sum them. That is the summation. Once you sum them, you have the HI, which is the polymer risk indices. So it's not for just only PET, it's for the individual polymer. You sum them, you have the HI. Then in my results.
Sorry, Doc, may I interrupt quickly? And I'm not referring to the one particular PET, I'm referring to all of them. Did you Did you identify every single microplastic for its polymer type?
For the particular river?
Now, did you identify every single microplastic in terms of which kind of polymer it is?
Dr. Father, can you please?
Do you get what Spark is trying to ask?
No.
That in each of your sample, were you able to identify every single polymer in each of your samples?
No. There are some ones that were not identified. I excluded them from this presentation. In my study, in my paper, you see them others that will not be identified. So, but I excluded them from this presentation. My paper is available online. Once you look at it, you see the different type and others that was not identified. So other, but I just excluded them from for the purpose of this presentation. Did I answer the question?
Yeah, thank you. I think Spark, are you okay with are you satisfied with the response, or you need some?
I think I'll read the paper, because let's say for PET, did you find 450 PET microplastic particles, or did you only process 450 particles for polymer type? For example, if you collected 10,000 microplastic particles, but of that you took a sample, and of that 450 were PET. So your polymer risk index is the 450 may not be representative of all the microplastic particles if they were not all identified in terms of polymer type. But thank you. I'll find the paper, Doc. Thank you very much.
Yeah. All right. Thank you.
Find the paper, you can still write me. Any question?
Can we take? I think there's a question from Dr. Sheniat. Please, can you allow her to ask the question quickly?
They did answer it, and they haven't raised their hand, so I think we can just say, basically, the question was from Seniyat that did you consider age in the plastic risk? Because obviously they do think that because there's a higher surface area, maybe that has more contaminants that can be attached to them, or they're more toxic versus maybe pristine particles that are used in toxicity that are maybe less toxic. I know there is a bit of debate, so I think that question is around considering age in risk indices.
No, we don't really focus on the age. Model doesn't consider age. You don't need to know the age of the plastic. The only thing we need to know is this polymer there or not? Because if a particular polymer is old, it emits more compounds into the particular matrix that polymer is. So if it's emitting this particular compound, the particular compound is that particular compound. So the models address that. So it's not really focused on the age of the particle. What is there is just the type of particle, is the polymer there or not. So it doesn't really focus on age, but actually addresses that as well.
Okay, thank you very much, Mr. Enyoh. I personally will still have a personal interaction with you. I'm sure that if we have toxicologists here or ecotoxicologists, they have a lot of questions to ask, in what are the factors that you really consider in arriving at the risk, especially to human. And I think that's a very important aspect of this. And it's also very interesting that if we can have models like this, then we should be able to predict some of the effects of microplastic in our environment, especially, I don't know, that's peculiar to our own climatic conditions. So I want to thank Mr. Enyoh for the wonderful presentation and another eye-opener that truly we are also doing a lot in Africa, but until we project it this way, it may be difficult for people to actually know what we are doing. So thank you very much once again. And I want to say that next episode of this Club Talk will be coming all the way from the East Africa, specifically from Kenya. We are going to have one of our colleagues that will be making a presentation, and the details will be sent at the right time. So we also want to encourage everyone that is doing one study or the other that will really want to project it, and we'll be able to rub minds together and also collaborate. Should please get in touch with me or any of the PAN-microplast team members in order to get them listed for their presentation. So thank everyone. We meet next month. That's when? 5th of August. Yeah.
So I don't know what the next one would be, but stop recording, sorry.